Hello everyone, I'm Pragya Srivastava. I'm here to record a lecture on control system. The course code is KC 602 and presently we are discussing its unit 4, which is stability of linear control systems. So previously in my lecture, we have studied how the stability can be predicted, and there are a number of methods using which we can predict this stability, and few of them are like Raud-Hurwitz criteria. And presently in this lecture I'll be discussing the method called as root locus, and in unit 5 we will come across another two methods which are Bode plot and Nyquist plot. So Nyquist criteria to predict the stability. So that is how we will go ahead and proceed in this course. Coming on to the root locus, in my present lecture I will be discussing the introduction, the concept of root locus, angle and magnitude condition. We will come across what are these conditions, and then rules for construction of root locus, and after that we will be discussing numericals. Now, introduction. It is possible to adjust location of a closed loop poles of a system by varying the loop gain. So what do? We can of course change the loop gain, and we can make changes in the gain term, like we said HS, sometimes we call it GS. So since the nature of transient response is closely related to the location of closed loop poles, it is very important to know how they move in S plane. Actually, the poles do move, they move in S plane as the gain or some other parameter is varied. So when the gain k, let's say, changes from, the gain k changes from k equals to 10 to k equals to 20, there comes a condition when the location of poles also change. So we have to study, and we also know that the location of pole is directly dependent on the is directly changing the stability condition, or I can say that stability is directly dependent on the location of poles. So we have to study the variations and then the respective change in stability condition. So root locus is one technique where it is the locus of roots of the characteristic equation of a closed loop pole in S plane as a given parameter is varied from 0 to infinite. Let's say we are talking about k and we are varying k from 0 to infinite. And this technique was introduced by W.R. Evans in 1948. It is a powerful method to analyze and design the stability and transience of a control system. It gives the information about absolute stability as well as relative stability of a system. It clearly shows the range of stability for which the value of k, the particular range of k for which the system remains stable, the particular value of k for which the system is at the verge of getting unstable, that is called marginally stable, and again a new range of k for which the system will always be unstable. So it can be used to solve higher order algebraic equations. So this is a basic concept in which we can see that the open loop gain, why we are calling it open loop gain, because this is, let's say this is the open loop gain which is not connected and not dependent upon the feedback. It is just the open loop gain, and here k and b are some constants. Now this is the open loop gain, and sometimes we cover it, let's say considering it a negative feedback system, and we make it, the transfer function will become gs upon 1 plus gshs, and substituting the value of gs, that is k upon s into s plus sb upon 1 plus k upon s into s plus sb into hs. Hs is of course needless to say, it is a unity feedback system having the hs value 1. So 1 is here, and after rearranging we land on to the overall transfer function, which is k upon s square plus bs plus k. Now according to this equation, the denominator of the transfer function is the characteristic equation. So the characteristic equation is s square plus bs plus k. Now solving this equation according to Sridharacharya's method, we can have the different values of poles. different s values, they are nothing but the location of poles. So here we have got it minus b by 2 plus minus root over b by 2 square minus k. So let's say this s1, s2 are the location of poles, and this is my s plane. Here I need to plot s1 and s2. So can I plot s1 and s2 now? Answer to this question is no. I cannot plot it now. Why? Because I don't know the value of k and b. So let's assume some values of k and b. Let's assume that k is equivalent to b by 2. Let's assume k is greater than b by 2. Let's assume k is less than b by 2. So let's assume these things and find out whether the system will be stable for that particular assumption or not. So I'll be rewriting. Let me write the location of poles S1, comma S2 is equals to minus b by 2 plus minus root over b by 2 whole square minus k. So here comes the actual realization. So the first assumption is that let us consider that the k value is between somewhere 0 and b square by 4. So we have to assume a value where the k is where k is between 0 and b square by 4. So when this situation comes, we can see for this particular situation when the k value is between 0 and b square by 2, meaning that the overall quantity within the root over is greater than 1. So it means it is greater than 1, and adding that value, making the algebraic sum, we will have two real values. One goes with plus b by 2, one goes with minus b by 2. So we will be having two roots. We will be having the roots are real and distinct. In this particular condition, the roots are not the imaginary. They are real and two distinct. They are two different roots. So further, we assume that let's say k is equal to 0. At condition when k equals to 0, two roots will be lying at s1 equals to 0. Both the roots will be lying at s1 equals to 0. And another condition, s2 will be minus b, and they are coinciding with the open loop poles of the system. Let us consider the second condition. Second condition is when k is equal to b square by 2. So b square by 2, it means this quantity turns out to be 0. In this situation, we will be having two poles. We will be having two poles, and those poles will be repeated poles at the same place. So this will be two poles, S1 and S2, both of them will be at minus b by 2. So this is a particular condition. Next is, let's say that this value is greater than b square by 2. So this complete value which is within the root over becomes negative. So when we have anything within the root over and the sign is negative, so we have imaginary term related with that. So according to the imaginary term, the second term would be imaginary, and adding to that, we'll be having two complex conjugate poles, and both the poles will be having the real part as negative. So in that equation, we will be having two roots like this. So we see, depending upon the value of this k, sometimes these poles are at s equals to 0. In the first condition, let's plot the first condition with red. So first is at 0 and another is at minus b. Let's call the second condition with green, where we have repeated poles at the same position. And next we have the third condition where the poles are at conjugate. So if I draw this movement, what I'm doing, I'm actually increasing the value of k from 0 to infinite. So the position of roots, they are changing. So let's draw a loci of the position of poles. And I will take some other ink. Let's say I'm taking this orange. So from k equals to 0, it's starting here. From k equals to 0, it's starting here. At k equals to b square by 4, it comes here. And then one pole will go here, another pole goes here. So can I draw it like this? So this yellow curve is nothing but the movement. So from the least value of k, it started from the two extremes. From the least value of k, it started from the two extremes. As the value of k is increasing, till the value when k becomes b by 4, it has come and both the roots are meeting at minus b by 2. The moment it exceeds b by 2, the roots will split and they will come into the conjugate positions and they will split like this. So for at infinite, this branch will go till infinite, another, the bottom branch will also go till infinite. So this is how the roots are moving. And since the roots are moving and we are drawing the loci out of that, we call it root locus. So I think I have made the condition clear that how value of k can determine and change the positioning of the roots. Now, from here I can also predict the stability of the system. In this particular question, k will always have value between 0 and infinite. He will have a value, any set of value in between 0 and infinite. So for any value of k, 0 to infinite, I can see that my system, my poles, they are never ever moving to the right hand side of the S-plane. No, they are never moving. They are not going into that domain. They are starting, they are meeting, and then they are splitting in this direction. They are never entering. So if they are not entering, it means for any value of k, you no matter you go to infinite, it is not entering into the right hand side of the S-plane. So it means my system can never ever be unstable for any value of k. Let us imagine any case where what is happening. Let's say the root locus. Let's say the root locus is moving in this direction. Let me take another ink. Where the root locus is starting, and it is going like this. So after this particular cutoff, this, of course, this will go to infinite. So this particular region, this particular area, when the root locus is crossing the j omega axis, the system becomes unstable. So here we can predict the stability. So for all those values which are on the left hand side of this yellow curve, signifies the stable system. For all the values of k for which the root locus moves on the right hand side of the S-plane, the system becomes unstable. So this is how the root locus helps us to determine the stability of the system. So this is all about the concept. We have to learn that how one can make a root locus, how one can design a root locus, how one can predict the actual path of roots, how we can make the root locus. So this was the concept, and I think I have covered this as well. Moving on to angle and magnitude condition. The point of root locus branches satisfy the angle condition. So angle condition is used to know whether the point exists on the root locus branch or not. We can find the value of k for the points in the root locus branches by using the magnitude condition. So we can use the magnitude condition for the points and which satisfies the angle condition. So angle condition is, from the characteristic equation, let's say this is the characteristic equation, and we can also write it as -1 plus 0j. We don't have any imaginary part in that. So from that, the phase angle can be tan inverse imaginary by real. So imaginary is 0, real is -1. So here we have this particular angle. So angle condition is the point at which the angle of the open loop transfer function is an odd multiple of 180. So for angle condition, for angle condition at a particular point, the angle of the open loop poles should be an odd multiple of 180 degree, and we'll be finding this. And if it is an odd multiple, then of course the root locus will exist there. And coming on to the magnitude condition, of course we know that for GSHs the magnitude is root over s square, -1 square plus 0, which is equal to 1. The magnitude condition is a point at which the magnitude of the open loop transfer function becomes 1. So this is very simple, and nothing more on that. We will study more about magnitude and angle condition in Bode plot. Moving ahead, we straight away come to the rules to find and to make or construct the root locus. So the first rule is to locate the open loop poles and zeros in the S plane. Whatever is the question, let's say we have been given s plus 2 upon s plus 3 upon s plus 4. So what we have to do, we have to, let's say this is -1, -2, -3, -4. So first of all, we have to locate, this is a 0, then we have to locate, this is a pole. So this is what we have done. We have just located the poles and zeros. This is the first condition which we do. Then we have to find the number of root locus branches. Now, according to the basic concept, we can see that how many zeros are there. Let's say I will write, for this condition we have 1 0. And how many poles do we have? We have 2 poles. Actually, is it the correct thing which I have written? 1 0 and 2 poles. No, this is actually incorrect. Here also, it is not 1, it is 2 actually. We have the same number of poles and zeros for any system. Only the point is, we are not representing that one pole because that is lying somewhere at infinite, and that 0 is having no impact on my system. So I'm not representing it. That is what we will study, and the root locus will only satisfy, the root locus will only prove this statement, that for the particular condition we will study in this root locus only, that yes, we are having the same number of zeros and the same number of poles. And since, because we can have a same condition like this, let's say we have 3 zeros and we have only 2 poles, then we can also see that this 2 is wrong. We have actually third pole 2, but that third pole is lying somewhere at the infinity, and that is not having any impact. So we have to just delete everything, and we have to start studying the rule 2, which is number of branches. So actually, let's say we have for a system we have let's say for any system, yes, let's say for any system we have 2 zeros and we have 3 poles. So how many branches will be there? For the first thing, the root locus will start from poles and will terminate at zeros. So it has 3 poles, it will start from 3 different poles and it will originate at 3 zeros. 3 zeros Do we have 3 zeros? No, we don't have 3 zeros. Those 2 branches out of this 3, these 2 branches will go and meet these 2 zeros because they are present in the S-plane. This one pole will go and meet at infinite because the third pole is at infinite. So it is very clear that 2 branches will start and terminate on the S plane itself, but that one additional pole will terminate at infinity. So talking about number of branches, of course, whichever is more, that will signify the number of branches. In this, presently, we will be having 3 branches. And moving ahead on this, we will study more on the rules of construction of root locus in my next lecture. Thank you.